Hey guys, here we are for Chapter 13, Section 2. We're going to talk about the sustainability of groundwater. Yeah, I know, I'm wearing a jacket. It's cold out there this morning. Anyway, here we go. Groundwater withdrawals, where we're taking it out of the aquifer. So we have surface water, that's going to be our rivers, lakes, streams. And then we have groundwater, our aquifers by and large. And we do also have deep aquifers, way below. These are way below the lakes and even underneath the ocean in some cases. Those we don't have very good access to. So we're talking about groundwater withdrawals. This is the basic aquifer that we're pumping water up from. Now in some areas, we are pumping the water up faster than it is renewed. It rains, the water sinks down through the ground. We call these recharge zones, the area with which the water is able to seep down into the ground and refill the aquifer. The problem is we can pump the water out faster than it can leak down through the ground. Because it rains and it doesn't immediately make it to the aquifer, it can take a long time to seep all the way down there. And this is because of a lot of widespread drilling of wells. Mainly farmers. Remember, 70% of our water is going to agriculture, crops, etc. So it's not that farmers are the only people doing it, that's just the lion's share of it. They have accelerated this aquifer over pumping. They need water to irrigate the corn, and corn is just a really thirsty crop, fairly big, right? So it takes a lot of water. And because of this, our water tables are falling. Saudi Arabia, somewhere in the 90s, began pumping water up out of their aquifer. This is a deep aquifer in order to grow wheat to feed the people in an area of the desert. I'll stick the picture up here. So on the left-hand side, you see where it's just desert, and then on the right-hand side, you see all the little green circles. Now, it might be hard to distinguish circles, but you got this little green area. Well, that's where they were growing wheat. Well, down in the bottom of that, you can see part of that is already going back to brown. Well, in 2008, they had depleted the major deep aquifer and have since had to just let it go back to desert. They pumped out the water in a matter of about 10 years that took over 1,000 years to fill. It's depleted, and all they can do now is wait for it to recharge again. But it's going to be hundreds or 1,000 years before that aquifer refills. Now, when it comes to withdrawing groundwater, pumping it up from the ground, as with everything, there are trade-offs, right? There are advantages and there are disadvantages. So let's take a look at some of them. First off, it is useful for drinking and irrigation. It's filtered down through the ground, it's pretty clear water, we treat it. But overall, now if you're a farmer, you can pump it straight up and spray it. If we're drinking it, we treat it. But still, it's available almost everywhere. You drill down deep enough, you hit the water table. It's good for drinking and exists almost anywhere. It's renewable. As long as we're not pumping it out faster than it's raining and recharging, it's a renewable resource. And it's cheaper to extract than most surface water. Surface water we may have to pump off for a while depending on where your farm is or where the town is. So it winds up being cheap, easy, and available. Disadvantages. If we over pump it, that's the main disadvantage. We over pump it and then it's not renewable. We can pump it out faster than it can refill by nature. Also, we get sinking of land, subsidence. This water is providing structure. As we take the water down, the land above it can often drop or sink. And here in Florida and lots of places, China, all over, you get sinkholes. This is where the aquifer gets depleted and the land subsides, it drops. Now, that area is no longer aquifer. It's been filled in by dirt, so it can't support water anymore. But anyway, the subsidence is there. And some of our deeper aquifers are non-renewable. We have aquifers up near the top of the water table, but some of the really deep ones, they're not renewable, not remotely in human lifespan or scale. And pollution of them can last for decades or centuries. The picture there at the bottom is showing like a septic tank. We have a septic tank underground. Well, if the septic tank gets a hole in it, these things are made of metal, they'll rust out, and then the sewage leaks out and it makes its way into the aquifer. Well, once an aquifer is polluted, it's polluted for centuries. You can try to pump all the water out and let it recharge, but once again, it winds up not being renewable. Now let's look at a case study. We're going to do a case study, the overpumping of the Ogallala. The Ogallala is the largest known aquifer. It is what irrigates our Great Plains. It is back up under a lot of these Great Plains states, Kansas, Nebraska. It even goes all the way down into the area of California. It is a very slow recharge. This area doesn't get as much rain, so the rain that does get there eventually seeps its way down into it. The water table out there is dropping. The water has been pumped out of it some 10 to 40 times faster than its actual recharge rate. This is an issue. Once again, 20 times faster. It's natural capital. There's a lot down there, and we can extract into that natural capital for a while. We can pull out more than we need, but eventually we have to let it recharge. If we don't, it can be gone virtually forever, way outside of a human time scale anyway. Now, government farm subsidies actually have resulted in further depletion. We pay farmers to go out and start a farm, so they go to a dry area because they know they can pump water out of the aquifer. So our subsidies are leading to faster depletion of the aquifer. If we weren't paying the subsidies, they wouldn't decide to farm there. They go somewhere where there was better access to more surface water. We can only take so much out of the ground sustainably. And once again, that's the name of the game. Biodiversity is also threatened by this. As we pull water out, well, this in the aquifer, that basically is part of the water table. It eventually leaks out. This is where we have a lake or sometimes a wetland. And if the water table goes down, the wetland dries up. As we've learned in other chapters, wetlands are amazing sources of biodiversity. All kinds of wildlife comes in, everything is drawn to this wetland, and when the wetlands dry up, the biodiversity goes with it. And as we know from this point, the greater our biodiversity, the greater things are. Take a look at the map back here. This is just showing where this Ogallala is. So we look right in that section of the Midwest. Now, we're looking at sort of two different maps, if you will. Let's talk about the whole map of the United States. Red is areas where it's dangerously low. We're at overdraft. We're pulling more out than it has. It's the danger areas, if you will, all through that Midwest and then over also into California. Notice Florida is all yellow. This is moderate. This is overdraft. We're pumping more out than it can actually sustain. We're not truly in a danger zone yet, but we are at the Ogallala. It's a danger zone. Often the inset, well, it's showing up just that in the Midwest. These are showing the areas in terms of meters that the water table has dropped. Red is getting up into the 30s and down into 15 to 20, and kind of that orange then moving into yellow. So they're just areas where we are pulling way too much water out of our aquifers. Because of overpumping, well, it limits our food production, and then it raises prices. Once again, as we're trying to pump the water out, there's less there. We have to build bigger pumps, or buy bigger pumps, if you will, to get the water up. A pump can only have so much suction. You got to get a much bigger pump to get deeper wells. So it costs more money to drill, to dig, and pump the water out. Food prices go up. As food prices go up, we widen the gap between the rich and the poor. And a big gap between the rich and the poor is not what we're after. We want more of a level playing field, if you will. We also get land subsidence. Like we talked about, you pump the water out of the aquifer, the land tends to settle. We can get a sinkhole if it's in a small area, but if you take a look at the picture of here with a person standing next to it, looks like a phone pole or a power pole, a utility pole. Well, this is showing the height of the land. Up in 1925, it might be really hard to see from there, but right near the top of the picture, that's where the land was in 1925. And it shows where it was in like 75. And the land where he's standing is where it is today. The land used to be that high up. We pumped that amount of water out, and the land is slowly sinking. As the aquifer goes down, the land sinks with it. Subsidence. It's not always just a sinkhole. Entire huge tracts of lands under these big aquifers all subsides and sinks down. We have seen this type of subsidence in the San Jose Valley. This is a picture where this is in California. We've seen it in Mexico City. It's just one of these issues. Also, overdrafts near coastal regions, then we wind up getting it contaminated with salt water. We pull the water out and it goes down. Seawater tends to leak back through these sort of recharge zones and fills that gap. And in areas, especially around here in Florida, some of our aquifers have become polluted with seawater, making it no longer any good to drink, and it depends on the crops. We can't even use it to water crops. And once we deplete the groundwater or it becomes contaminated, we have to switch to other sources, and there's only so many out there that we can assess. Now, some of our solutions to this, what do? Well, there's just prevention. Use water more efficiently. Lots of us wind up doing water waste, and even in irrigation, we're 70%. A lot of our irrigation practices are not very efficient. We drip systems, putting the water directly in the ground instead of spraying it on the top. Spraying it on the top, we get a lot of evaporation, but if we're pumping it out of the ground and then it's evaporating, it's still part of the water cycle, but we don't have it available in the aquifer because it can take longer than a human lifespan for the aquifer to refill, making it non-renewable if we're pumping it too fast. Subsidizing water conservation. There are subsidies out there. A lot of times their subsidies are doing things that winds up harming the environment. Instead, let's make sure our subsidies are paid to places that are doing water conservation. We give you a subsidy if you're doing it in a sustainable way, as opposed to we're just paying a subsidy to get the end product. Doesn't always work the best. We need to limit the number of wells, period. You have to regulate wells. If you have a well, how much water is pumping out? We've got to know how much we're taking out so we can regulate what is left and have a better idea of keeping it, once again, sustainable. And we really need to stop growing water-intensive crops in very dry areas. Corn is one of these. Corn is a very thirsty crop, if you will. It needs lots of water. We need to stop growing corn in the really dry areas. We need to grow it where it's closer to either some natural rainfall or surface water. Control, some of the things where there's prevention and there's control. How do we prevent it? Some of those. Let's talk about some ways that we can control it. Well, we can raise the price of water, and nobody really wants to hear let's raise the price of anything. But if we're paying more for water, we're going to be more careful with the water that we're using. So once again, full cost pricing can come into play here. We need to tax water that's pumped from wells that are near surface water. If you're putting a well in, but there's access to surface water is renewable. The hydrologic cycle, the water cycle is doing its thing. We need to pull water from surface water instead of the aquifers when at all possible. And it'd be pretty hefty taxes if you're choosing to pump it instead of taking it from surface water. Rain gardens in urban areas where you can catch the rain and divert it into areas where we can use it. And also we need to start using some permeable paving materials. Our cities and urban areas have grown. Well, these are on recharge zones. The rain falls, if it hits the ground, then it seeps down into the ground and fills the aquifer. But when it's hit its roads and pavement and it's diverted off into surface water, back into our rivers, etc., it's not recharging. So we need to develop pavement, if you will, asphalt, things that are permeable so the water can seep back through and recharge. This is one way that we can help control the water making it down. Now we've talked about our aquifers. We have readily accessible aquifers, and then we have deep aquifers. Now, some of our research has shown that these deep aquifers may contain enough water for billions of people for centuries. Remember, fresh water we have available to us like 0.0 or 0.024%. Of all the fresh water, 1.7% is locked up in glaciers and ice caps. Another 1.7% is in these deep aquifers. Now, we have some concerns. We believe there's enough water for the human race, once again, billions of people for centuries. However, we don't know enough about them. First off, these are non-renewable. These are aquifers below even the oceans, but well below our lakes. So we have kind of an aquifer here, which is our water table. The top end of it is our water table for lakes, etc. And then we have non-permeable ground, solid bedrock, but up underneath that we have another layer of aquifer, very, very deep. Little is known about the impacts of pumping it out. You know, if we wind up pumping, we don't really know what would happen, something we haven't tapped into yet. We have no international treaties. Most aquifers tend to be contained under countries. They're much smaller, like even our largest known is only this area of the Midwest. It's not the entire United States. Well, these deep aquifers, you could drop one down, but the deep aquifer is under many, many, many states. So coming up with some sort of international treaty, you know, it's one country is going to pump out billions of liters a day and another country is only going to pump out 100 liters a day or 1,000,000 liters a day. There's a big discrepancy there. So we need some sort of treaties, and there aren't any. Cost of tapping it are unknown. This would take massive pumps. This is government level operation practically to be able to pump this water up. They're so deep down. So the cost of it is unknown. And it could well be that that water is contaminated. It's down deep enough, it could be contaminated even with things like uranium, heavy metals, mercury, etc. So it's there, we know it's there. However, when it goes down to trying to tap into it and access what is there, we have a lot of unknowns, cost and contamination just being two of the really big ones. Oh, that wraps it up for section 2. Come back and join me next time when we talk about increasing our freshwater supplies. Take care, guys.